Hello community, great that you're back. We have a look at the latest AI research called Luffy. Two papers, difference is they are about 1 month apart. This is here March 21st and this is here from yesterday, April 21st, 2025. We talk about here reinforcement learning. Here we look in this paper here in particular about how good are even the base model in the reasoning capabilities and how we can optimize this learning to reason under off-policy guidance. And reading this ahead, what is off-policy guidance? So let's jump into the topic. The first paper tells us, you know these aha moments when you see in the reasoning trace of a reasoning model that the model says, now I understand, hey, let's try something else. This is what they found out, that the DeepSeek version 3 base model already has this. So they already have a strong reasoning capability in their pre-trained model, in the base model. And you do not need prompt templates. This is what they call, and even the Q1 2.5 base model exhibit these strong reasoning capabilities. So isn't this great? This fits perfectly what I told you. Reasoning capabilities are in the pre-training and in the continued pre-training of our LLM. They looked also at GRPO and they found here a better optimized GRPO. This is great when this happens. And they tell us here, we develop now OAT. This is a new model with their new GRPO implementation. And they say, hey, look, this is our benchmark. So let's look here at the benchmark here at AIM24. And you see this new OAT 07B. Look at this beautiful performance here, 43.3%. Now, interesting. 1 month later, by this paper here, also here, this is here National University of Singapore, Singapore Management University, and this is now Shanghai AI Laboratory and Westlake University and Chinese University of Hong Kong. They have now also AIM24, but look at this. The same model, OAT07B, but guess what? Suddenly they say now the performance is only 31.7 because they have now their own model. And their own model is in AIM24 a little bit not so good, as this model, as the OAT07B model. So interesting to see if you compare the paper of 1 month, that this is the original paper from the original people of OAT with their original data. And 1 month later, you already see here that this is reduced significantly. And I don't know why. And just whatever, we will come back to this, and just remember this is AIM24. Now, if we look at other one like AMC test, 62.7 and this 61.6, so there are differences, 30.1 and 29.8, so those are minor differences. So just remember AIM24 has a significant difference because look, the new Luffy 07B has a performance here of 29.5. And imagine we would compare this here to the original AIM24 here with 43. So something is happening. Never mind. We are interested in the theoretical approach. So let's start with this video and let's have a look what's happening. We are here in zero reinforcement learning. This is a very specific technical terms. What does it mean? Applies the reinforcement learning to the base model directly. There's no supervised fine-tuning in between. So eliciting here the reasoning potential using here the model's own rollouts. Fundamental limitation is worth highlighting. It is inherently on policy, meaning constraining here the learning exclusive to the model's self-generated output through iterative trials and feedback. So zero RL is directly RL on the base model, on policy is the own policy self-generated outputs. And despite showing here promising results, the zero RL is bound here by the base language model itself, especially for complex reasoning. And the paper, you know this paper, we've talked about this. This is from Harvard University, the echo chamber. Reinforcement learning post-training amplifies behavior learned in the pre-training and nothing else. There's no emergence, there's no intelligence coming out here of the dark. Zero RL is bounded here by the performance and the training of the base model, the pre-training model only, full stop. Now, of course, as in AI research, we ask, hey, how can we empower LLMs to acquire now reasoning behaviors that surpass the initial cognitive boundaries of the pre-training. What we have to do, if this fails, come on, there must be another solution. Huh? And I talked a lot about distilling here reasoning traces from a more powerful AI via supervised fine-tuning here of a weaker LLM. So we transfer, if you want here, the intelligence of a reasoning trace with supervised fine-tuning. You remember the DeepSeek provided us here open source. They have here the DeepSeek R1, but they also give us the R1 Distilled Q132B model. So DeepSeek is so nice to do this open source, and we have those models. But of course, if I want to do this with O3 by OpenAI, which is closed up and is not providing the distilled models, I was asking here, hey, can we use here methodology from UC Berkeley to get those smaller models that I can run maybe locally? Now, just to be clear now, I have to be a little bit precise with the terms I use. The process is best described as imitation learning and also falls under the umbrella of transfer learning, especially knowledge distillation. But important, it is not an off-policy reinforcement learning. And this will become important real soon. And you might ask, why? So what is now exactly the difference? And whenever we ask something, what is the difference? Let's start with a definition. Imitation learning. The goal is to make a smaller LLM, the learner, mimic the behavior and the reasoning steps and the tokens of the powerful AI, the expert. We use supervised fine-tuning. We have a supervised fine-tuning loss function. Normally, it is somehow related to the cross-entropy of the system, and we understand this. Transfer learning, knowledge gained by one model, the powerful teacher AI, transferred to another model, the smaller student LLM. Under the reasoning traces here generated by the teacher model, yes, distilling the reasoning capability as manifested in the traces from the large model to the smaller one, and we have supervised fine-tuning process is the mechanism between this occurs. So why is it now not also an off-policy reinforcement learning? Think about it. We have a missing reward signal. Off-policy reinforcement learning relies on learning from experienced tuples where we have the state, we have the action, and we have the development of it. So to maximize now a cumulative reward or defined now by a particular environment feedback or a task success is now our main goal. In contrast to this, the supervised fine-tuning process described does not involve an explicit reward signal, but there is nothing. Yeah? We have in supervised fine-tuning only the loss function. And the loss function is purely based on the matching, the expert output token, the likelihood maximization, and it is not to achieve a higher reward based on a task completion, a feedback from the environment. Let me just stress that this is important. Let's switch to hardware. Let's say we are here in doing here we're producing something. I want that the process chain of the production is followed 100%. I don't want that the AI says, hey, now I come up with a new idea how to do the production different. No. This is timed. I know exactly the cost. This is a reliable process. It is tested. I have a quality assurance in this process. So I want that I use supervised finding to have a rigid task following in my production line. So I go for supervised fine-tuning. Really, this is what I'm looking for. Reinforcement learning is a different beast. Yeah? So the learning algorithm supervised fine-tuning uses standard supervised learning optimization, a gradient descent on a cross-entropy loss. Now, the offline policy R uses here specific techniques like Q-learning or the act-to-critique methods. I have multiple videos of this with important samples designed to handle here the learning optimal behavior from reward signal coming back from the environment using data generated by a potential different policy. We have a policy optimization problem on a mathematical point of view. So this means the goal of the off-policy reinforcement learning is optimality according to the reward function that we define, while the goal of the supervised fine-tuning is fidelity to the expert trace and only to this precise expert trace. Switch to hardware. You don't want that your production line suddenly says, hey, and now I do something completely different because I think I can do better. So, supervised fine-tuning, you want to stick to the process rules. Beautiful. So when you supervise fine-tune a small language model and reasoning traces of a larger language model, what is happening? It is imitation learning. It is transfer learning. It is not off-policy reinforcement learning. Although, and now this is a point where you mix up something, the data is itself off-policy. Why? Because you don't use the on-policy data of the model itself. You use off-policy data from a stronger model, from a cloud-based, a huge LLM. Therefore, the data are off-policy, but the learning paradigm is supervised imitation, not reinforcement learning. So, careful, we are not going for the characteristics and the defining functional of the data, which are off-policy, but the defining characteristic is here, the learning paradigm. Sometimes people mix it up. Great. Supervised likelihood maximization, I know you're going to ask for this. It's simply the mathematical objective that we use to achieve the goal of supervised fine-tuning of generative AI models. Now again, the goal of a supervised fine-tuning is to adapt the model's behavior to produce outputs that are really similar to the desired outputs provided here in the fine-tuning dataset. Remember, supervised fine-tuning is to fine-tune for a single particular downstream task. You want in your hardware production facility that this downstream task is followed precisely. And if you have the control unit for the hardware production in your production line, you say, listen, this is the defined process by myself. Or if you are in medicine, you know how to produce a pharmacological substance. And you want that this is the process. It has to be followed 100%. So you do want rigid traces. Now, if some people now complain about rigid traces, they make a basic mistake. Because what they want is something completely different. They are talking about new knowledge. They are talking about new reasoning that is based on new knowledge. And they try here to achieve this with supervised fine-tuning. And we, you and I, we know this is not the appropriate methodology. So just to be clear, this is task-specific. If we want to generate new knowledge and integrate new knowledge, we know we have to go with pre-training and continued pre-training. So how we do it then here if we are in zero RL? You know this question, how can we empower the LLMs to have reasoning behavior that surpass the initial model-specific boundaries? Now, imitation learning, no? You have traces now from DeepSeek R1, the big brother, and you say a little 32B model, yes, learn it. But of course, this locks here, the little LLM, into some rigid reasoning models that are deducted from DeepSeek for a very specific task and that impede further, if you want, free learning. Or, and now this is the main new idea of today, you say, okay, I have here the on policy, the self-generated outputs of the model. What if I now simply I incorporate off policy knowledge alongside the on policy learning? Because then I have the on policy self-generated outputs and the off policy reasoning traces from an R1 for my little 32B model, like we discussed in this video. And this is exactly this new methodology, and it's called Luffy, learning to reason under off-policy guidance. And this is now a new, unified zero RL paradigm. So we stay within zero RL applied to the base model directly, but now we have on-policy and off-policy integrated. And isn't this great? So based on the conventional zero reinforcement learning methods such as GRPO, Luffy now introduces off-policy reasoning traces from R1 and combines them with, let's say, a Q1 own on-policy rollouts before the computation. Little, tiny, insignificant problem, we have an immediate entropy collapse to one solution. Oh, and you say, okay, so we encounter a problem. Never mind. So what is the problem? Naively combining now the off-policy traces can lead now to an overly rapid convergence and a complete entropy collapse of the complete system, causing the model to latch onto superficial patterns rather than acquiring here some real, genuine reasoning capabilities. And if you think about it, it's clear, no? So, we have to come up with some new ideas. The results, if we do then Luffy, and if we read here at the end of the publication of Luffy, they say, hey, we found a way, no? It encourages the language model to imitate here the high-quality reasoning traces from R1 while maintaining the exploration of its own sample space, limited here by its own reasoning traces. So, Luffy found a way, and now we ask ourselves, how was this possible? Now, easy. The answer is the authors introduce a policy shaping via a regularized importance sampling, and the effect of this new methodology is to amplify the learning signals for the low probability, yet crucial actions from our big brother under the off-policy guidance. So you say, okay, so in my policy optimization problem, a mathematical optimization problem, I have new regularized importance sampling, and there is some shaping happening here to my policy. What is this shaping? Just want to tell you here what is the best possible result that we achieve with this new methodology. Luffy achieves here clear improvements, it's the word of the authors, of 7 points better on average compared to the previous RL0 methods. 7 points. Okay, it's not a lot, but better than 2 points, no? So let's have a look what's happening. You remember the good old GRPO, our formula here with the clipping and everything, and you say, yes, beautiful, no? If you're not really familiar with this, I have a specific video for you. It is called AI Math Explained, the easy way. And here in this video, you'll find all the explanation what you see here in the next 10 seconds on my screen. Now, you know, we do have here a mixed policy GRPO. No? So we have here now the part of the off-policy objective and the on-policy objective. So here is now the intelligence, if you want, from the R1 traces we bring in. And here is the on-policy objective, here the intelligence from the whatever the model can generate from its own reasoning capability, having here a feedback from the environment. And as you see, we have already a normalization factor. Beautiful. Now, if we now think about this, and they found a theorem, and they say, yeah, we introduce now an importance weight, W, which is clipped by a boundary, never mind, and they say, you know what? While the mixed policy GRPO incorporates now off-policy rollouts successfully via importance sampling, a new practical challenges, a new problem emerges. The importance sampling accelerates the convergence, but significantly reduces the exploration. We don't want this. We want exploration. We want exactly this beautiful, delicate equilibrium, exploring here with our flashlight the dark room in front of us, and exploiting here, if we found here a specific object with our flashlight in the dark room in front of us, then we want to investigate this object further, because maybe it's a car that is coming closer. We want that our AI is able to find new reasoning patterns, but if it found one, really go deeper and find not only the reasoning pattern, but the solution of this reasoning pattern. So we want to do both at the same time. However, as it turns out, we have again the entropy collapse even much faster than on the on-policy reinforcement learning. So this is not what you want. Your entropy collapse is now almost immediately. So indicating increasingly deterministic rollouts and a diminished capacity for exploring diverse reasoning trajectories. But you want your AI to be exploring every possible solution in the solution space, not just say, okay, and now I converge on one solution within milliseconds. No, you want that the AI tries to understand how many problems exist, how many different perspectives exist to my problem, and then I choose one solution. So you want exploration of diverse reasoning trajectories. So, okay, you have a problem, so you find a solution, and you ought to say, hey, to address this particular issue now, we introduce now a policy shaping. Here we are now with the shaping parameter gamma. We have regularized importance sampling, a technique that reweights here the gradient of the off-policy distribution to enhance the learning from the low probability tokens that come in via the R1 reasoning traces and are off-policy distributions. And now we just do here a little bit of twitching to the gradient of this off-policy distribution. We reweight something in a particular mathematical way, so to enhance the learning from the low probability tokens. So we have a clear aim, no? There's nothing complicated about this. We just say, hey, we have to focus more our low probability token. We have to bring them into the calculation stronger. Otherwise, they are just left out in the dark. Great. So, a loss function with policy shaping, if you are a little bit interested more in the mathematical form that we then code, this will be the new code base for the implementation. Yeah, we have, of course, for both papers, I show you a GitHub repo. You find the code over there, enjoy it, you have a deep dive. I just want to explain here the basic idea. So this policy shaping here, beautiful is happening. Illustrate the meaning of the policy shaping function f. Derive the gradient of the off-policy objective here, and as you see here, f, the gradient of f here, and here this term, we can solve this term, and the term is the importance sampling. So somehow we have now a policy shaping, and if we do some mathematical, not tricks, but further computations, then we can say, okay, this can be rewritten in a form where the shaping function kind of reweights now the gradient. This is exactly what we started. We wanted that the shaping function reweights the gradient, and now with this mathematical formula, we achieved our strategic goal. So you see, mathematics just was a tool that we used to find here a piece of code that we then just fed into our neural network calculation. What we do, we improve the learning from unfamiliar yet effective decisions from the off-policy traces of R1. We want to integrate here the reasoning of R1 into the little 32B body of knowledge. And with this shaping function that reweights here the gradient, this is what we achieve. So mathematics just to follow our ideas. Shaping function reweights the gradient to assign more importance to the low probability actions, thereby improving the learning from unfamiliar yet effective decisions from the off-policy traces. Simple, no? Yeah, absolutely. Unfortunately, there's the next problem. But never mind, we can find a solution, no? We're researchers. So Luffy, and I'm not saying fluffy, Luffy experiences here more frequent clipping compared to the on-policy reinforcement learning, which now again can suppress the learning from the high quality of policy traces. So if you look now deeper into the mathematics, you see, we have here the problem that our clipping here is really strong, powerful. And the authors of the paper said, hey, to address this, we remove here the mathematical term of the on-policy clipping to allow here for greater flexibility. It's a brave move. Just say, okay, cross out this term. Never mind. You see, we see that this is causing problems. We have more frequent clipping, but we want to have those off-policy traces. So just delete this particular term here that we have in our reinforcement learning, in the basic reinforcement learning formula that is encoded here for our calculation. So, brave move. Let's have a look at the facts. It is a beautiful paper, really. It is a full paper. It is great. And you know what? Normally you have here on page 1 a beautiful abstract, and you have here a visual guide that tells you here the core elements here, the new stuff, the new insights. Beautiful. But you know what is really makes this paper outstanding? Page 2. Because on page 2, they describe the authors how they see the world of AI. They show us here their principal understanding, the complexity of their thinking, the problems they encounter, and they give us here a 1 paragraph or a 2 paragraph explanation, what problem they are tackling, what is their approach in their research, what is their solution, and how valid or what limitations exist for their solution. And I can tell you, if you get a little bit used to this, the quality of page 2 is the determined factor for me personally to judge a paper if I want to read it or not. Because if I see that the authors have really references to papers that just came out a week ago, and I'm not saying, yes, 2 years ago or 3 years ago. No, if you say, hey, last week there was a paper, and I think I can make a reference to this, and I tried to integrate this data. Also, it's brand new. There seems to be a correlation regarding whatever. If you have people that are really here, up to the leading and bleeding edge of AI research, they show it to you in page 2, and this is what I like. And this paper here, I do like especially. Now let's come here to the last page here of this paper. And this is where they show you now the result. No, this is if you imagine you're a venture capital meeting, no? And then you say here at the end of your presentation, and now, ladies and gentlemen, I show you now the most convincing argument that you should invest in this startup company. And here we have it. This is it. And this is a very interesting chart. Let me take 2 minutes to have a look at this. So at first they give us here an LLM with a temperature. This is beautiful. Because, the higher the temperature, the more creative an LLM is. But we are talking here about a mathematical trained Q1 2.5, 7 billion free trainable parameter model. So normally, you would say a mathematical model, you do not want here high creativity, but you want here solid, non-creative mathematical models. So interesting. They give us here the temperature. And you might ask, why? Well, you're going to love this. And then you have the accuracy here for a particular benchmark. And now read this. They are giving us says, hey, our benchmark is not for our data here, not for one benchmark, but from our set of benchmark, we select 2 benchmarks. AIM24. Do you remember AIM24 from the beginning of this video, what I told you? And AMC. So they cherry pick. And of course, they are the authors. They want to present themselves in the best light possible. I got it. So they cherry pick here these 2, and they say here, yeah, and beautiful, intelligently, they say we don't go here for posit 1, but posit 8. So our K equals 8. Great. So they read the last paper from the last week. They knew exactly what to do, and I love this. And they say, look, this is not a difference. So we have here in yellow, if you want here, the line that if you would interpolate it would go up somehow, off on policy reinforcement learning. The classical that my last videos were on this. And then in, what is this? Blue, they have here aligned with supervised fine-tuning. Something completely different. And you would say, if you ignore this here, you would say, okay, so we have this here. Great. And then they have in red their model. They knew Luffy, beautiful. And of course, it is better than the rest. Let's have a look at this. Now you see, because we do have the temperature, I would interpret this, okay, Luffy in red and supervised fine-tuning in blue or teal or whatever this is. I would say from the temperature of 0 to 0.6, let's say that this red here is interpolated here with this, and this teal or blue line is interpolated with this, and I ignore this outlier here for the moment. You see, they are almost parallel. They are almost here real close at the same level. But this would not be what you want, no? Because you want to show that your model is better. So they integrate now cleverly. Yeah, but you know what? At temperature 0.6 to 1, so when I ask the mathematical model to be more creative, here in the higher creativity area, now we see a difference. Because up at temperature 0.6, I would say they are so close. There's, no, for me, in a simple way, no difference between those models. Eh? So to point out how much better their model is, no, they introduce here the temperature scale, which is not really standard, but a good idea, great idea. They really make clear this is our benefit. If you go to creative mathematics, which is a contradiction in itself, but never mind, then our model shines. And you see supervised fine-tuning decreases. Now I have to tell you, for my particular use case, I use mathematical models rather at low temperatures because I want here rock solid mathematical deductions. I don't want that my mathematical AI says, hey, I explore some brand new ideas. I go a little bit crazy. Let's see where this leads us. No, I'm rather a conservative guy. So you see why it's now so important to have this slide here with the temperature, because otherwise I would say, for me, for my use case, supervised fine-tuning and this new methodology, which is rather complicated if you want to have a deep dive, a mathematical deep dive, and it is a rather human-induced term-specific optimization of the gradient function with different reweighting optimization problems, formulated in a friendly way. Okay, so they are almost identical performance now. But you know what? There are even some, yeah, okay, let's come to the conclusion. So Luffy, beautiful now, and now they say in their conclusion, surpassing both on policy, reinforcement learning, and supervised fine-tuning. Now, at this, I would say, wait a minute. So Luffy here is, of course, the author said it's the best, no? Surpassing on policy RL, okay, and supervised fine-tuning, okay. This is a strong statement. Show me the data. And you know what? Something is missing. Have you noticed it? Because the classical solution is missing, no? That we have on policy RL and supervised fine-tuning. Where's the curve that shows me if I do the classical supervised fine-tune and then the reinforcement learning? I know I cannot add this. This would be the wrong operation. But if I see that the on-policy reinforcement learning is already here close to 70% plus, and our, where is it? Supervised fine-tuning is here. Let's take the worst case, 70%. Yeah? I think they could contribute here some additional performance, maybe. But since there's no data, I don't know. I can't tell you. So they had the data and they decided not to run this with supervised fine-tuned and reinforcement learning because, and this is now a pure hypothesis, theoretically the performance would have been above their red model. So you see, whenever you see those final results, be a little bit careful, have a closer look, and you immediately understand where we have some weak interpretation or some specific visualizations here for the venture capitalist. And this is you, the user, if you decide if you want to implement this methodology. But this is on a 7B model, and I think this is great and this is the right way. Maybe even go a little bit higher, 32B model. But you know, there's also the open source community that says we want to run models locally on our infrastructure. So maybe 7B is already quite a lot, no? So for this, for your particular value-added benefit watching this video, I have something for you. But at first, let's say this, no? This is here an exact vote, just to make it absolutely precise here. So compared here to its supervised fine-tuning counterpart here, our method means Luffy, here the authors, achieve a notable improvement of 2 points on average, providing a more robust and effectively alternative for distilling knowledge from stronger language reasoning models achieved through supervised fine-tuning. So they tell us, we're better than supervised fine-tuning. We are plus 2 points better than supervised fine-tuning. Now I have to see 2 single points is not a lot of you say, hey, now you should invest in me. And you remember at the very beginning, I told you there was a discrepancy here in the AIM24 data of, you remember OAT, the 7B model here with the optimized GRPO? Now I had a closer look at the data, and now you can say, okay, you know what? In an AI summarization, you would get this. You would get a final answer, and I've tried it with 3 different models, but take your model, please. And they will give you the result. Hey, compared to the supervised fine-tuning, this method achieves a notable improvement. And it is really a better, more effective, more robust alternative for distilling knowledge from stronger LLMs. But is this really true? Or is this just an interpretation of a particular configuration? And they are so beautiful, and I love this study. They are transparent, and they give you the data, and they give it even for a 1.5 billion free trainable parameter model. And I use this, and thank you for providing this data. This is the standard everybody should have. So they say, okay, the Q1 2.5 math, 1.5 base, and the instruct model, and they give us here the data. And look, here we have AIM24 and AIM25 and AMC. And you remember their main result was AIM24 plus AMC. And then we have here pure supervised fine-tuning, the classical. Then they have the old-fashioned standard on-policy reinforcement learning with the solution that the model generates itself without the injection of R1 traces. But you have here a reward function, and the reward is the feedback from the environment. It tells you whatever you did as an action here, as a reinforced learning model, was good or bad. And depending if this action was successful or not, you get a positive reward or a negative reward. Great. And then here in the last line, we have Luffy. Yeah, the new contender. And now you know what? If you choose, like they did in their presentation, to combine now AIM24 and AMC, you know what? Look. SFT is identical in AIM24 according to their data, 15.2 to 15.2, but in AMC, Luffy is better, 43.5 to 46.8. So if you combine those two now, you see you have a better improvement here. Luffy is better than supervised fine-tuning. But you know what? Let's play here the advocate of the devil. If I choose now, and I'm free to choose as an author of a paper, AIM25, the more advanced AIM, and I choose Minerva as a benchmark data set, now the situation changes, no? Because now supervised fine-tuning is the better one, and supervised fine-tuning is also outperforming Luffy here on Minerva. So whenever you see here that the final result is a set of your particular benchmarks added together, and you say, why? You know why. So just to make sure here, né? And now, since I want to provide here more value to my viewers on this YouTube channel, I ask you, would an AI summarization point this out to you? So here you have my logic, and I hope this will help you. You understand that reasoning traces require knowledge. So this means whatever is your base model, your pre-trained model, if you notice it is not up to date with the latest knowledge, let's say on medical, you have to do a continued pre-training to update the knowledge of a very particular domain. Reasoning traces implement reasoning for a very specific task. And this is supervised fine-tuning. And it is absolutely task specific. And I want that this task is followed exactly. I told you the example here of a production online company. You want here that it is a rigid learning, that the task is followed exactly, 100%. You don't want here any freedoms of creativity. You are cost optimized. So this means supervised fine-tune when you do it, when you do have to find a very specific task for your company, for you, and you want that this task is followed. You have a lot of training data, and this is great, and you need to make sure the domain, the knowledge in the domain is there. If the knowledge is not there, your specific task instruction, your reasoning here, will simply fail. So this is supervised fine-tuning. And then you have the reasoning traces, and they can be aligned or, let's say, enforced for a very specific model behavior that you want to achieve. So this is the classical one. You remember PPO from, I don't know, years ago from OpenAI, reinforcement learning. Now we have GRPO, the group relative policy optimization. We have DPO, TPO for test time compute scaling. So this is here something if you want to modify the behavior of the model. And I want to give you here an example. The colleagues in the US, I'm sitting here in Europe, so I just hear what they tell me here about the US. You remember Llama 4. And now the latest, what I heard is that Llama 4 is indeed a good model. That it has the performance. There's only one thing. You have to massively train it. And there is now some ideas, and this is just, if you want, rumor, this is not facts, that the reason for this is because Llama 4 also supports in Meta their complete, if you want, social platforming. And currently there was the idea, not by the researcher, but simply by the management, Mark, to adapt here the orientation of Llama 4 more to the current geopolitical, if you want, orientation of the USA. So the ruling, the dominant doctrine, the political doctrine, and the model should reflect this. Now, just imagine a thought experiment. If your pre-training data, if you continued pre-training data, if you supervised fine-tuning data, and let's say you orient yourself on the internet, on the social platforms, maybe you have a beautiful mix of opinions. And then you say here, maybe the management, I want that Llama 4, particular for the social media appearance and managing your complete social media, how to say this, algorithms and preferences. I want that the new Llama 4 model follows a particular political ideology. Then, at the end of the training, you try to bend the complete model. Now, of course, a lot of things can go wrong. Just imagine if now the new data that you try the reinforcement learning on are not really linguistic, semantically compatible with the pre-trained knowledge, with the supervised fine-tuned knowledge. Imagine now you try to bend them all in a direction that is not supported by the data, that is only supported here by the new management orientation for a new ideology. Whatever it is, I don't care about the ideology. I just want to tell you, if there is indication that with massive retraining of Llama 4, and I mean, the amount of money is much above 1,000 US dollars, you can make Llama 4 a model with a quotation mark good reasoning, with a performance that is average now. This would be an indication that something happened really at the end of the training process of Llama 4. And if my scientific colleagues tell me that there is now this idea that you have to massively retrain and modify Llama 4, and then it is a good model, this would be here a beautiful example, how sensitive this step-by-step process is. And if you want at the end to bend the model in a direction that is not supported by data, the whole model can lose performance massively. And maybe this is the case that happened with Llama 4. So if you are familiar with the situation in the USA and you know more about this topic, hey, why not leave here a comment in the description of this video? So you see, beautiful new publication here. Great. They also have, of course, here a GitHub. This is the GitHub. README file was just updated 39 minutes ago. You have everything over there. And if you want, they even give the acknowledgement how they built their models, what they used here for running the models, the MAT verify for mathematical reasoning, evaluation, open source community here, dataset backbones, including Numina, MAT Open, or MAT 220K, the datasets that they are available for you by Hugging Face. And this is the citation, so I think a beautiful paper. I highly recommend you have a look at it. And if you're interested in more of those videos, hey, why not subscribe? And I see you in my next video.